pure hash functions. The first talk is entitled Nearly Optimal Property Preserving Hashing by Justin Holmgren, Liu Minghao, and Lakaya Tyner. And Lakaya will give the talk. Lakaya, the floor is yours.
Thank you for the introduction. Like you said, my name is Lakaya Tyner, and I am presenting on nearly optimal property preserving hashing. This is again joint work with Justin Holmgren, Minghao Liu, and Daniel Wicks. So I'm going to begin by giving you guys some background on property preserving hashing, and then go into the coding theory that we will need for our constructions, and then introduce our constructions and talk a little bit about bounds, and then I'll end with some open questions. So what is a property preserving hash? We have this hash function H, which takes as input an n-bit string X, and then outputs an n-bit string H of X. And then we can consider some binary property, P of XY, which is equal to 0 if the property does not hold, and 1 if the property does hold. And we say that H is a property preserving hash for this binary property P. If given H of X and H of Y, we're able to determine if P of XY holds. Okay, so this NM property preserving hash family for some predicate P consists of this family of hash functions curly H and the following algorithms. We have our SAMP algorithm, which samples one such hash function H from that hash family. And then we have our eval algorithm, which takes as input a description of that hash function H, and then H of X and H of Y, and outputs 0 or 1. Additionally, we must satisfy the following properties. We have correctness, which basically says that the probability for any XY chosen, any worst case XY chosen a priori, the probability that the eval algorithm outputs something different than P of XY is negligible. If we want our property preserving hash family to be robust, we must also satisfy this additional property, which says that correctness holds even when X and Y are chosen adaptively by an adversary who has seen some description of our hash function H. Okay, and if we want to understand better the difference between a non-robust and a robust property preserving hash, we can consider the difference between universal hashing and collision resistant hashing as it pertains to the equality predicate. So a universal hash is exactly a non-robust property preserving hash for the equality predicate because it satisfies this correctness property. Okay, and a collision resistant hash is exactly a robust property preserving hash for the equality predicate because it satisfies additional robustness property. Okay, so why do we care about studying property preserving hashing? What if we wanted to compare objects beyond equality, let's say by some similarity metric that we may want to define? Apple attempted to do this with their NeuroHash application, which was intended to detect child sexual abuse material on the cloud. Unfortunately, they had a few issues with collisions, such as these two images. But I think studying robustness or how to make this particular application or similar applications robust is still useful. Okay, and then property preserving hashing can also be useful for facial recognition when determining if two images are of the same person. In this particular work, to compare objects, the property that we study is the Hamming property, which determines if the distance between two strings x1 and x2 is less than or equal to some threshold t. Okay, and then we also mentioned this gap Hamming predicate, which determines if that distance is less than t, less than or equal to t, or greater than or equal to this 1 plus delta times t for some constant delta. And the reason that we study this Hamming property is because it serves as a basic unit of measure, and it could lead to us understanding better some more complex metrics in the future. And in fact, it is currently being used as a common method for measuring the similarity between feature vectors and machine learning. Okay, so this idea of studying the robustness of property preserving was introduced by Boyle, Levine, and Vaikuntanathan in 2019. And in this work, they introduced two constructions for the gap Hamming predicate. The first was from standard collision resistance, and the second was from the sparse SIS assumption. After we have this work by Fleshhacker and Simpkin, which introduced the first exact Hamming property preserving hash construction that we have. And it was introduced, or it was based on this new assumption called the Q-strong bilinear discrete log assumption that was introduced in that same work. More recently, we have this other exact Hamming construction from Fleshhacker, Larson, and Simpkin that was based on a more standard assumption such as SIS. So an immediate question that we can ask after this is, can we get some better compression on the output size of M? And can we get a construction for exact Hamming on some more minimal assumptions? And the answer to that, as we show in this work, is yes, we can do both of those things. So in this work, we present two constructions for the exact Hamming predicate, the first based on SIS or discrete log, and the second based on standard collision resistance. Okay, and the output size of our first robust construction is approximately equal to h of t over n times n, where this h of t over n function is Shannon entropy. And this is strictly less than the output size achieved by prior works. And in our work, we prove a lower bound that shows that this output is actually optimal. Okay, and then we also get optimality from standard collision resistance for our exact Hamming construction. For the remainder of this talk, again, I'll go over some concepts from coding theory that we will need, and then move on to explaining our constructions. So the first thing from coding theory that we will need is this NKQ error correcting code, which is defined by this matrix G. If we multiply this matrix G by some message M that we may want to transmit, we get a code word C. And the hope is that if some error were to actually be inflicted on this code word C during transmission, depending on the number of errors, we'd be able to successfully recover this code word C. In order to do that, we need this parity check matrix P over FQ as well, which has this special property that P times any code word is equal to the 0 vector. Okay, and a process for recovering any error that may have occurred during transmission is known as syndrome decoding, which we will be using in our constructions. Okay, so let X equal C plus some error vector E. Then given the syndrome S equals P times X, we can successfully recover the error vector E such that this Hamming weight of that error vector is less than or equal to T. Okay, and then doing some substitution, we can also notice that that syndrome is equal to P times that error vector E. And using this fact, we will be able to recover our error vector. Syndrome-less decoding is a similar process. Codes that are syndrome-less decodable are able to handle more error. And the difference between this and syndrome decoding is instead of recovering a unique error vector E, we recover a list of possible error vectors such that the size of that list is polynomial in N. Okay, and a common metric for efficiency for our error correcting codes is this rate, which is a ratio between the size of our message M and the size of our code word N. And we have this Hamming bound that kind of describes so ideally we want this rate to be as close to 1 as possible, but we have this Hamming bound that kind of describes how close to 1 we can ever hope to achieve. So it says that R is equal to 1 minus H of T over N, where again, this H function is Shannon entropy, and this is optimal. Unfortunately, we only have inefficient codes that meet this Hamming bound. Efficiently, we meet this slightly weaker Bloch-Zyablov bound, which is equal to 1 minus, which says that the rate is equal to 1 minus HBZ, where this HBZ term is slightly larger than Shannon entropy. Okay, so let's move on into our first construction, which is again a non-robust construction for the Hamming predicate that uses syndrome decoding. Let's remind ourselves of Hamming. We have this distance between x1 and x2, which is equal to the Hamming weight of x1, or x2. And Hamming is equal to 1 if that distance is less than or equal to t, and 0 otherwise. We will also be utilizing a universal hash function for this construction of the form h of x is equal to a times x for some matrix x over Z2. And this satisfies this universal property, which says that for every x1 not equal to x2, the probability that the hashes of those two inputs are equal is less than or equal to 2 to the minus m. Additionally, this hash function satisfies this homomorphic property, which states that a times x1 minus a times x2 is equal to a times quantity x1 minus x2. And this is a useful property that we will need in our constructions. Okay, our NM non-robust property preserving hash for hash family for Hamming. Let P be the parity check matrix of an NK2 code. We sample our hash function H and our matrix A, such that H of X is defined by P times X and A times X. In order to evaluate this, we let H of X1 and H of X2 be defined as follows. And then we compute the difference between those two syndromes, PX1 and PX2. We run syndrome list decoding to get our list of possible error vectors, such that for every EI in that list, P of EI is equal to P times X1 minus P times X2, and the Hamming weight of each of those vectors is less than or equal to T. Okay, and then if there exists an I in that list such that A times EI is equal to A times quantity X1 minus X2, then we output 1. Otherwise, we output 0. And the intuition behind this is we're treating the difference between those two vectors, X1 and X2, as the error that we're trying to recover. And so we run syndrome decoding to get a possible list of those errors, and we confirm if there does exist such an EI in that list that satisfies this relationship. If that is true, then we can output 1. And this basically reiterates, we know that security or correctness holds because if X1 and X2 are close, meaning if EI is indeed equal to X1 minus X2, then we will find that EI on the list. If the difference between X1 and X2 is greater than T, then for every EI in that list that we recover, A times EI will not be equal to A times X1 minus A times X2. We also define a couple corollaries in this work that define the upper bounds for the size of our output, m equals to n minus 1 plus lambda. And this is using an NK2 linear error correcting code that can efficiently list decode up to T errors. As I mentioned previously, we only have inefficient codes to meet this optimal Hamming bound to get our output size equal to Shannon entropy time n plus lambda. If you want efficiency, we have codes to meet this slightly weaker Bloch-Ziebaugh bound. It's not too far off from the Hamming bound, but there is a bit of a difference, a small difference. Okay, and here's the output size for that, for using those codes. We can get a non-trivial compression for up to a constant distance of T equal to big O of n. And we can upper bound the size of our output, m equals to big O of T log n plus lambda. But for large T, our Bloch-Ziebaugh bound allows us to do even better because the log input or the log n term in that output size actually disappears. Okay, here's our first robust construction for Hamming. This construction basically shows how to take our non-robust construction and make it into a robust construction. So they're really similar, but they do have a key difference, which I will explain. Instead of using that universal hash function that I mentioned earlier, I'm going to replace that by a homomorphic collision resistant hash function. And the two constructions that we currently have for homomorphic collision resistant hash functions are from discrete log from Pedersen and from SIS from ITI. Okay, even with this change, we're essentially able to achieve the same compression as our non-robust construction. Okay, here's our second robust construction for Hamming. This is based on standard collision resistance, and we show how to take a gap Hamming property preserving hash from the BLV paper, that first BLV paper, and how to amplify it and make it into an exact Hamming predicate, or an exact Hamming property preserving hash for Hamming. So let's remind ourselves of the gap Hamming predicate. Let D of x1, x2 again equal to the Hamming weight of x1, x or x2. And then gap Hamming is equal to 1 if that distance is less than or equal to t, equal to 0 if that distance is greater than or equal to 1 plus delta times t, and about otherwise. Okay, so an NM robust property preserving hash for Hamming. Let H gap be that robust property preserving hash for gap Hamming from the BLV 19 paper. And then similarly as before, let P equal this parity check matrix for this NK2 error correcting code that can efficiently decode up to 1 plus delta times T errors. We sample our hash function such that H of X is defined by P times X in this H gap of X. In order to evaluate, let Y1 and Y2 be defined as following. We again compute the difference between those two syndromes, P of X1, P times X1 minus P times X2. Run syndrome decoding to retrieve a unique error vector E such that P times E is equal to P times X1, X or P times X2. And the Hamming weight of that error vector is less than or equal to 1 plus delta times T. And then we perform 2 checks. We output 1 if and only if our first check, which is the output of the eval gap function or the eval gap algorithm from that BLV construction. If that is equal to 1, and the Hamming weight of our error vector E is less than or equal to T, then we output 1. Otherwise, we output 0. And the intuition behind this is this eval gap, or the output of this eval gap algorithm will tell us whether or not our Hamming weight is greater than or less than or equal to 1 plus delta times T. If that is indeed if that is indeed true, then we only need to worry about whether or not that Hamming weight falls or the Hamming distance falls in between that gap. So the second check to make sure that the Hamming weight of that error vector E is less than T will catch that. In this work, we also study a new notion of randomized robust property preserving hash, or R2P2, for the Hamming predicate. And we're able to achieve a information theoretic construction as opposed to our deterministic robust constructions, which require at least standard collision resistance. Okay, to give you guys an overview of this construction, H of X is computed using a randomized process. And then an adversary A can choose our worst case X and Y after seeing a description of H, and then succeeds if eval outputs something different than P of XY. And something that's important to note with this particular construction, or this particular notion of randomized robust property preserving hash, with our deterministic constructions, an adversary is able to choose X and then see the output of X of H of X and then choose Y. In this case, that's not true. Because if the adversary is able to see the output of X of H of X, they can learn some knowledge about the randomness that was used to compute the output of the hash on X, and then in some way choose a bad Y that will enable it to break security. Okay, for our construction, we get this information theoretic R2P2 hash for equality from prior works, which is able to achieve an output size of O of square root n. In this work, again, we are able to produce an information theoretic R2P2 hash for the Hamming predicate that achieves an output size of big O of square root lambda n plus f of Tn, where this f of Tn is equal to Shannon entropy times n. We noticed when writing this paper that we're able to use tentative decoding plus a homomorphic universal hash to get a robust property preserving hash for Hamming. And then similarly, we use tentative decoding plus a homomorphic R2P2 hash to get R2P2 hash for equality to get an R2P2 hash for Hamming. Okay, and again, we get this equality R2P2 hash from prior works. In summary, this work produces or introduces one non-robust property preserving hash for Hamming, and then two robust property preserving hashes for Hamming. Our constructions are conceptually simpler than those introduced by prior works, and we're able to achieve a better compression under minimal assumptions. And we also studied this new notion of randomized robust property preserving hash for Hamming. And we are able to introduce an information theoretic construction and achieve optimal parameters. The open question that I would like to leave you all with. So for our robust exact and gap constructions, we can show that we can actually achieve an output size of m equals to h, that Shannon entropy minus little of 1 times m plus lambda. And this essentially matches for the non-robust exact parameters, but we don't know how to do any better for the gap gap Hamming construction as opposed to the exact Hamming construction. There's this work by KOR in 2000 that says that indeed for the non-robust gap construction or for non-robust gap constructions, we can achieve an even smaller output size of m equals to O of lambda. So for our final open question is, can we achieve a similar output in our robust gap constructions? Thanks for listening.
Thank you, Lakaya.
We have time for a quick question. I don't see a question on the Zoom, but people in the audience have a questions. Please line up to one of the mics on the left or the right. No? So to keep ourselves on time, let's thank Lakaya again. And move on to the next talk. See, no questions on the Zoom, but people on the Zoom are also clapping. The next talk is entitled Collision Resistance from Multi-Collision Resistance by Ron Rothblum and Prashant Nalini Vasudevan. And Ron Rothblum will give the talk.
Momentarily.
Well, yeah, sure. Take your time. I see the slides already on Zoom, but not just here in the room. There we go.
Okay,
Ron, the floor is yours.
oops. Okay, thanks for the introduction. Let me repeat it because a couple of minutes ago. So the talk is titled Multi-Collision Resistance, from Multi-Collision Resistance to Collision Resistance. And this is a joint work with Prashant Sudevan. So this talk is about sort of two different security notions for hash functions and what I think is a somewhat surprising relation between them. So the first one, or maybe the second one on the slide, is that of collision resistance, which is a property that I assume all of you are familiar with, very central notion in cryptography. And the other one is called multi-collision resistance, which I think many of you are familiar or otherwise can guess, but let's maybe start off by sort of defining these notions. So collision resistant hashing is ubiquitous in cryptography. These are hash functions that are compressing or shrinking which means that, they have a lot of collisions. But nevertheless, we conjecture that it is computationally hard to find collisions in these hash functions. And these are extremely prevalent both in the theory and practice of cryptography. So that's collision-resistant hashing. Recent line of work has studied a relaxation of this notion, something that's called multi-collision resistant hashing, which kind of comes to address the following question. Suppose you have a hash function in which it's possible to find pairwise collisions, but maybe it's hard to find three-way collisions. So three differing inputs that all collide on the same output. Okay, so that would be three multi-collision resistant hash function, or 3MCRH. Okay, and it's a relaxation. It's a weaker security property than CRH. And the question is, what is it good for? How does it relate to other properties that we're interested in? So let me be a little bit formal about the setup. So first of all, so Susmu talked yesterday about keyless multi-collision resistant hashing. Here we're going to be talking about keyed hash functions, which is the more, at least in the theory of cryptography, it's the more mainstream or traditional notion. So we're looking at a collection of hash functions. So this MCRH notion is parameterized by two parameters, T and L, both are integers. So we have our hash function that I think of it, or collection of hash functions, mapping n bits to n minus L bits. So L is the level of shrinkage that you have, or compression. And what we want from this collection of hash functions is A, that it's efficiently computable, and B, the security property says that if you look at any bounded adversary, polynomized adversary, if you sample a hash function from the collection at random, and you give the adversary a description of this hash function, the adversary basically won't be able to find a T-way collision. So a set of T elements, this is a set X, that all collide on the same output. Okay, so it's a different way of writing that. So that is multi-collision resistance. And just as a sanity check, note that if you take T to be equal to 2 and L to be equal 1, you get this 2-1 MCRH. So this would be an MCRH in which it's hard to find pairwise collisions, like a CRH, with 1 bit of compression. But we know that with CRH, if you have 1 bit of compression, you can basically get any level of compression that you want by composition. This turned out to be quite different when you're talking about TMCRH. Okay, so composition, if you start talking about more than pairwise collisions, then composition doesn't work very well straightforward. There are fancier ways, but they all increase the parameter T. Okay, so you have to be careful about both the amount of collision that you're interested in and the level of shrinkage. Okay, so we have this notion, and now we can ask ourselves, how are these two notions related? So obviously, MCRH is a relaxation, but to what extent? So I think having studied this notion for a couple of years now, it really looks like this notion of MCRH is significantly weaker. Okay, and even this very basic composition property is sort of evidence to that. It seems like a qualitatively weaker property. But somewhat surprisingly, nevertheless, for many of the key applications that we have for CRH, certainly in theory land, we can also do it using MCRH. Okay, so two notable examples. So if you look at constant round statistically hiding commitments, work by Komorgotsky and Oren and Yogev, and concurrent work by joint work with Berman, Degwaker, and Vasudevan, we showed that MCRH suffice for this. Likewise, if you're trying to build succinct arguments and something analogous to Killian's result, you can also relax. Instead of using CRH, you can use MCRH, shown in the same work by Komorgotsky et al. And also by Bitansky, Kalai, and Penef. So we see that for many of the applications, MCRH suffice, but it still leaves the question of, how does the power of these two objects relate? And what we show in these works is that actually in some regimes, you can go from this seemingly weaker notion and get a full sort of get a CRH. Okay. So let me sort of tell you what the results are. So the first main result, we consider three-way MCRH, so it's hard to find three-way collisions. And we're assuming that the MCRH that we start off with, has a shrinkage factor, which is slightly more than half. So you're outputting slightly less than half of the input size. And if you give me such an MCRH, then we're able to show that a CRH, a standard collision-resistant hash function, exists up to some asterisks up there, which I will explain in 5 or 6 slides. Okay, so we can do something interesting with 3 MCRH. Next question to ask is, what about 4? So with 4 MCRH, we can also do something similar, but we need the 4 MCRH to have better shrinkage. So it takes maybe n bits to n over 6 bits. Okay. And if you give me such an MCRH, I can once again construct a CRH. Okay, so we've managed to handle 4. What about 5? So unfortunately for 5, we don't know how to do this. So if you give me a 5-way MCRH, it's hard to find 5-way collisions. With any level of shrinkage, even if you're outputting polylog bits, let's say, I don't know how to get similar result. Okay, which was quite annoying. We'll get back to it towards the end. What we do know how to show is if you give me any TL MCRH, then we can construct from that a T prime L prime MCRH, where T prime is less than T. So we've reduced the size of collisions, but L prime is larger than L. So we pay in terms of the shrinkage. Okay, and the exact parameters for which it works are a horrible equation that I did not want to put on the slide. It's based on list decoding bounds for Reed-Solomon codes, but just as an example to keep so that you can think of. So if you start off with an MCRH in which it's hard to find collisions of size 100, and the compression is to like 10%, then we can build from that hash function in which it's hard to find collisions of size 50, but the compression is now only to 40%. Okay. So before telling you about how we do this, let me mention some prior work. So the first work that I am aware of that looked at this notion of multi-collisions is a work of Zhu, which is more kind of practice-oriented. And on the theory side, the first book is by Komorgotsky and Oren-Yogev, who showed a connection of this notion of MCRH to sort of Ramsey-style computational problem that we're looking at. After that, ironically enough, there was a 3-way collision of papers studying MCRH. So I already mentioned, I guess, the authors of all of these. And a little bit more recently, Komorgotsky and Yogev gave a construction showing how to go from MCRH into a notion called distributional collision-resistant hashing, which is a different sort of relaxation of collision resistance. So it's basically saying that it may be it may be easy to find worst-case collisions, but it should be hard to find sort of random collisions. Okay, so different relaxation, but this work is the sort of the inspiration or starting point for our work. Okay, so let me tell you a little bit about how we do this. And let me start with a sort of bird's eye view of how it's done. And even more basically, the technique here is sort of, I think, very different from what is common in cryptography. So let me start by describing what is common and how we differ. So usually in crypto, the way if you want to move from one cryptographic primitive to another, the way it's done is the following. So you're trying to move from A to B. So you take A, you throw in some algebra, sprinkle some combinatorics, you get the result B, and usually the construction uses A as some sort of black box, just using it as a subroutine. So that's sort of what you typically do. And then how do you argue security? You assume the existence of this red adversary for B, and you use it to construct this green alien adversary for A. And usually, the green adversary will use the red adversary as a black box as well, and probably also use the construction, the primitive A itself as a black box. So a construction that satisfies sort of this picture is called a fully black box construction. And if you think about it, the very, very large majority of constructions in crypto fall into this framework. But here we're going to be doing something different. Okay? So here's what we do, or like kind of a bird's eye view. So we start off with an MCRH, right? So it's hard to find large collisions. First step, we construct a candidate CRH. What do I mean by candidate CRH? A candidate CRH. So either it is a CRH or it is not. 2 options. If it is, great, we are done. So the more interesting aspect is what if it is not a CRH? If it is not a CRH, there exists an adversary, right? So there's an adversary. And what we do is actually use this adversary in the construction in order to build a different CRH. Okay? So the adversary itself is used inside the construction, not just inside the security reduction. And yeah, so the adversary is used also as a black box. What makes this construction non-black box is that the adversary that we have in the middle might be using the MCRH in a non-black box way, and we inherit that. Okay, so this is kind of the high-level view of the construction. And this proof strategy has some repercussions. So first of all, it's non-constructive, right? So if you come and tell me that you have an MCRH and you give me the code, I will not be able to tell you, here is my CRH. I can prove to you that one exists, but I cannot specify what it is. And the reason is, I have this candidate CRH, and maybe that works. But if it doesn't, then there's an attack, and I don't know what it is that specifies my actual CRH. So it's non-constructive. I can prove that a CRH exists, but I cannot sort of point it out to you. So that's one issue. The second is that the construction is non-uniform. So recall that usually in cryptography, we model adversaries as non-uniform circuits. And because we are using the adversary sort of constructively, we inherit the non-uniformity. So our construction itself will be non-uniform. If we're talking about uniform adversaries, then this would go away. And lastly, kind of more technical point, because an adversary, a typical adversary in crypto is only required to successfully break the primitive on infinitely many input lengths, now our construction will only work on infinitely many input lengths. So we only get infinitely often security. So just going back to the result slide, what this asterisk was actually hiding is that the CRH that we get is only infinitely often secure, and it's non-uniform. Okay, so that's sort of the high level. That was the bird's eye view. Let's go sort of to the worm's eye level, kind of briefly. So I will focus only on the first result, going from 3M CRH to CRH. So suppose we start off with a 3M CRH that has this compression factor of L. We're in addition going to be using some other non-cryptographic hash function family G, same input length. And we'll construct a new hash function family F. So G is non-cryptographic. It's based on some algebra or something. Don't worry about it yet. We construct a hash function family F, which basically just consists of the concatenation of H of X. Remember, H is the MCRH. So H of X comma G of X. Okay, this is a new hash function family that we constructed. We call it F. And now we ask ourselves, is F CRH? And either yes or no. If yes, great, we can go home. So the more interesting answer is when it is not a CRH, which means that there's an adversary that breaks it, right? So F is playing this role of the candidate CRH. So we have an adversary that breaks F, which basically means that given description of H and a description of G, our adversary is able to find a pair of distinct inputs that collide both under H and under G. That's what our adversary does. And for simplicity for this talk, let's think of the adversary A as working on all input lengths and working with probability 1. Handling imperfect adversaries requires some additional ideas, but I won't have time to cover that. So adversary always works for this talk. Okay, so here's sort of a naive attempt to use A to find larger collisions for H. So let's run, we're given a description of H. Let's run A on some particular choice of G. We get a collision under H. And now let's run A again using the same H, but with a different G. And that gives us a different, maybe, collision under H. So that's pretty good. We have two collisions. We'd like to combine them. So what we basically want is to try to find G and G prime so that these two pairs collide, basically that H of X1 is equal to H of X1 prime. And if we are able to find such a pair, G and G prime, then we violated the security of H intuitively. So which means that it should be hard to find such G and G prime. But that means, so we're saying that it's hard to find a pair of distinct inputs that form a collision. So that kind of indicates that A itself is collision resistant. Okay, so going into a little bit more detail, we're going to construct, using the insecurity of the candidate CRH, we're going to build a CRH, which just works as follows. So its domain is the hash function family G, and its output is again n minus L bits. And what we do is just on input little g, description of a hash function, we run our adversary, get a collision under H, and output the value of this collision. Okay, so this is, and I claim that this is an actual CRH, honest to God CRH with asterisks. So let's assume that it's broken, right? Assume that there is an attacker that violates security. That means that given H, this adversary can find distinct G and G prime that form a collision under this F sub A, this new hash function that we've constructed. So what can we say about this collision that was found? So it's just parsing. If I run A on input G, I get this collision X1, X2. collision for the original first candidate that we have. And when running A on input G prime, we get a different collision, X1 prime, X2 prime. And what do we know about these guys? So because they're a collision under the original F, it means X1 is different from X2, but it collides under both H and G. And we know that the same holds for the X1 prime and X2 prime. But because we have the collision under F sub A, then we know that H of X1 is equal to H of X1 prime. Okay, so we seem to be in fantastic shape because we found a four-way collision, right? We have that H of X1 is equal to H of X2, equal to H of X1 prime, equal to H of X2 prime. But you'd be somewhat suspicious because we haven't used any property of G yet, right? So the catch is that no one guarantees that these four inputs are distinct. For all we know, it could be the case, for example, that X1 is equal to X1 prime and X2 is equal to X2 prime, which is a problem. We need for them to be distinct. So looking a little bit more closely, notice the property that we have. We know that G is different from G prime, but we have a collision of both X1 and X2 under G and X1 prime and X2 prime under G. What if we could design our function class G so that for every distinct pair of X1 and X2, so for every X1, X2 versus X1 prime, X2 prime, there is at most one function G so that they forms a collision, so that X1 and X2 are a collision under G. If we could have this property, then we could never have sort of this case that we're worried about. So the functions G would guarantee this. So we just need to design G to have this property. And staring at this property for enough time, it seems a little bit reminiscent of stuff from I don't know, elementary school. So we have this property that if you look at any two distinct lines, they can collide on at most one point. Right? So that is the way that we will design G is to take the input X or the pair X1, X2. We will view it as lines. The hash function G will be sort of parameterized by a point on the line. And the evaluation of G on the line is outputting the value on the line. Okay. How am I doing on time?
You have 5 minutes.
5 minutes. Okay.
Well,
so
I mean, you're standing in between the people here in lunch.
yeah, exactly. So I won't go into
if
more
there's
details.
writing breaking out. Then,
Yeah. So I won't go as I'm standing between you and lunch. I won't go into more detail. But basically, an extension of this, geometric fact to finite fields is what we use in order to design our hash function G, and that is how we can guarantee that you get at least a three-way collision. Okay. So sort of to summarize again the main results, we show that in these regimes, we can use the existence of MCRH to get CRH, the collision-resistant hashing, with this asterisk. Let me mention maybe just that for the general result, instead of using lines, we use low-degree polynomials. And interestingly, the property that we need from low-degree polynomials is sort of bound on their combinatorial disk decoding. That's for the sort of more general result. So let me conclude with some open questions. So one thing that would be great is to get rid of some of these at least annoying qualifiers. So maybe something that it's tempting to do is try to get rid of the infinitely often by some idea, or maybe the fact that it's non-constructive. Something you might try to do is try to use a combiner or a universal construction. We tried, we failed, but you are encouraged to try as well. As previously mentioned, if we start off with a five-way MCRH, we don't have to go to CRH. We can go to, I forget whether either 4 or 3, but we can sort of go on all the way down to a CRH. So getting something for 5 would be fantastic. After we do that, we try to handle larger constants and eventually even super constant values of t. That would be great. Another thing that's interesting is whether these non-black box techniques are inherent. So there was a result by Komogotsky and Or and Yogev that sort of showed this, but a gap was found by Bitansky and Degwaker. So currently, we don't know a black box separation. It would be nice to sort of understand the picture of whether non-black box techniques are necessary. And the last two are a little bit more out there. So, it seems like a strange but powerful, at least in our context, technique. Can it be used in other settings? One place in which, would be very tempting to try is to, resolve this huge open problem of getting collision-resistant hashing just based on one-wayness. but it looks like our technique is not sufficiently strong because all of this technique sort of relativizes. So the type of oracle separation that Simon gives also rules out this kind of proof technique. So yeah, I think I'll conclude here and happy to take any questions.
Okay, thank you, Ron. So we have a few minutes for questions. Please line up to one of the two microphones in the audience. I do not see any questions on Zoom.
Over here.
Okay, I think we have a first question.
Yeah, thanks for the talk. I wanted to ask about the L parameter. So basically you showed that for 3 collisions, you need something that outputs, you need a hash function that outputs less than half of the bits.
Right.
So is there a bound on this? Can we
Yeah.
do something better?
Okay, so our construction needs this property, but moreover, it's related to the, so if you try to follow our technique exactly and try to build a better function class G, then you will not be able to. You'll be sort of our technique, the limit to n/2 is inherent to the technique. So even if you try some other this simple, so relatively simple lower bound based on the singleton bound, it shows that if you try to follow this approach, then n/2 is necessary.
Thanks. I think Evgeny has a question. Yeah, go ahead.
Maybe you alluded to it, but I guess for collision resistance, you have kind of domain extension. Once you can try to compute by one, collide, save 1 bit, you can save more. So here I can see that Merkel-Dunbar has trouble, hasn't been studied.
Yes, it has. And there's a very nice result by Nir and Omer and Yael showing, so they were looking sort of more at Merkle trees, and naively it would sort of blow up exponentially. And I think, or more than exponentially, and I think in the result, it blows up only exponentially in the depth, which is not too bad. So
you're saying there are results, but somehow you cannot.
There are results, but you pay. You pay less than what the naive payment would be. You pay in terms of like the parameter T.
So they change T.
Yeah, so T increases, but not as bad as you would like naively think. Yeah.
So in this result, I mean, so you're saying both the results and your play with both T and L is just your
right. So that's what you would try to sort of do a zigzaggy thing where, but at least for 5 it doesn't work. We tried obviously and it doesn't work. And more generally, we try to combine to do sort of a zigzaggy thing, and we weren't able to. So the loss that you get from one is not covered by the other.
But like in terms of preserve, kind of preserving T, somehow it's not natural. Natural thing
right.
Seems to change.
I have no idea how to do something that preserves T. It's a great question.
Yeah. Any other questions? Actually, like I had a quick question. So I'm trying to see the intuition here a little bit, right? So if it's easy to find a collision for an iterated hash functions, then it's easy to find multi-collisions as well. That's this result of Zhu that you mentioned. So what's the intuition here? I guess if you say it's easy to find collisions but difficult to find multi-collisions, we're not looking at iterated hashes then.
So I think it's somewhat, we're not looking at iterated hash functions. We're looking at a sort of abstract setting. And I think it's somewhat different because we're saying, we're giving some particular candidate collision resistant hash function. And we're saying if it is easy to find collisions there, it's not that it's easy to find multi-collisions, but on the contrary, we're going to take that tack and use that tack to build something else that is secure. So yeah.
Yeah,
and,
thanks.
Yeah.
I guess this is a good time to wrap up the session, and let's thank all speakers.